Okay, today we're going to talk about changes of state and equilibrium and phase diagrams, which is some of the stuff that our next lab will be dealing with. We'll be looking at the changes of state. So we have the phases, and when the phases change, it's a change of state. Now, is change of state a physical or chemical change? Physical, right? Because we're not changing the chemical compound that's in the mixture or whatever. We're just changing the state that it's in. So when we get to equilibrium, is the condition in which two opposing changes occur at equal rates in a closed system. It's like some molecules may be melting, but some of them could be freezing. And so when they're going at the same rate, then it's called equilibrium. When it's a closed system, that means that matter is not entering or leaving. Energy can, but the matter is not entering or leaving. So you aren't getting more matter, you're not getting less, you're not losing matter. So the point at which the change of phases are at the same rate as the equilibrium, which is what that just said up there. So an example, is with water in a closed system, if the energy of a water molecule is high enough in liquid water, if that at the surface, if that water gains enough energy, it's going to leave the surface of water and become a vapor, become a gas. But there's some water molecules that are vapor already that get close enough to the surface of the water that they get attracted by the other water molecules and become part of the liquid water. So when the rate of the water molecules leaving the surface and the water molecules joining the surface of the water are at the same rate, that is equilibrium. So to get vapor, the liquid must gain some sort of energy. Usually it's in the form of heat. So the liquid has to gain heat energy to become vapor. For vapor to become liquid, vapor has to give off heat energy to become liquid. So it's reversible because the vapor can go back to a liquid by losing the heat energy. Liquid would gain heat energy to become vapor. And it will remain at equilibrium until some sort of change occurs. And so when there's a change in the system that causes a shift in equilibrium, that is called Le Chatelier's principle. So when a system at equilibrium is disturbed by the application of a stress, so it could be a change in temperature, a change in pressure, it attains a new equilibrium position that will minimize that stress. So I think we have an example here next. So if we change temperature, so if we're at equilibrium, we change temperature. If the temperature is increased from 25 to 50 degrees Celsius, the system will respond. So will we have more liquid or more vapor form? More vapor will form, right? There's going to be more evaporation. So that's why we say the forward reaction is favored, because we're going to get more vapor. So to go from liquid to vapor, that would be a forward reaction. If it would have decreased from 50 degrees Celsius to 25 degrees Celsius, would you have more liquid form? So that would be more vapor is going back to liquid, so that would be the backwards reaction, or the reverse reaction is favored. So kind of think through that process. Okay, concentration is something you can change, like you can increase the salt concentration in water or something like that. But the volume increases. So the concentration of vapor will decrease because, let me draw a picture here. Maybe. Oh, is it going? Okay, so let's draw a beaker of water. I'm going to make this beaker black. So here's our beaker. I'm going to draw two beakers. So this will be before, and this will be after. So let's say before we have some water. And let's say we have, these are water molecules, the blue right here. Okay. And it's salt water, so I'll put some salt in there. But let's just say we have a few ions like that. But afterwards, if I increase the salt concentration, I'm going to have and then my water molecules are still here. At the surface of the water, so at the top of the surface, at the top of the beaker, which the before or after has more water molecules actually at the surface? Before, right? Because there's not very much salt. It's more likely that there's more water molecules at the surface than salt, since there's not much salt compared to the after. So there's more water molecules available to go into the vapor form compared to this situation where there's more salt. So after you if you change the concentration and increase the concentration, the amount of concentration of vapor will decrease because there's not as much water molecules at the surface to evaporate. Okay? So it will shift to the right because on the right, the forward reaction, we got more, decreases. The evaporation rate will stay the same, and the equilibrium will shift to the right. So that's what that means there. Okay, equilibrium vapor pressure is when the pressure of the vapor above the liquid is equal with the atmospheric pressure. So the vapor pressure is just the pressure that's exerted by the vapor on the liquid. And this will be important for when we boil a boiling point. We're going to need to know the vapor pressure. But it increases as temperature increases, because as you increase temperature, we said we get more vapor. And if there's more vapor on top of the liquid, there's going to be more pressure pushing down on the liquid. And so that's how the vapor pressure increases. We increase the kinetic energy, so we increase the number of molecules that can evaporate, so that increases the pressure. Okay, and there's a difference when we talk about evaporation between volatile and non-volatile liquids. Volatile liquids are liquids that evaporate really easily. Can you think of a liquid that evaporates very easily? Actually, water is very slowly compared to. So water would be more of a non-volatile liquid. It's kind of in the middle, but alcohol, like rubbing alcohol, evaporates really fast, which is why when you put it on your skin, it feels really cold, because it's evaporating so fast. It's taking energy from your skin. So rubbing alcohol is a very volatile liquid. Water is kind of in between, because it does evaporate just by sitting out, but it's not near as fast. Non-volatile liquids that evaporate very slowly, like oil or something like that, would be a non-volatile liquid. The reason why they evaporate slowly is because they have strong attractive forces, so they might be more polar. Their molecules are holding each other into the liquid and not letting molecules escape as easily. So boiling occurs when we have the conversion of a liquid to a vapor within the liquid as well as at their surface, like we talked about yesterday. The difference between evaporation and boiling. Evaporation is vaporization that occurs at the surface of the liquid, And then boiling occurs either at the bottom or in the middle of all that liquid. It changes to a gas and then bubbles out. So the boiling point is when the equilibrium vapor pressure equals the atmospheric pressure. So once you've gotten enough evaporation take place, because at first when you're boiling a pot of water, don't you see steam kind of rise off of it? And that's the vapor, at the evaporation occurring at the very top. There's vapor coming off the surface of the water. Once the vapor pressure is equal to the atmospheric pressure, then it will start to boil. So once it starts to boil, all the heat goes into evaporating the liquid. So it's going to stay at the same temperature until that liquid is all evaporated, and then the vapor can increase temperature. What's the normal boiling point of water? 100 degrees Celsius, which is what in Fahrenheit? 212, right? And that's at standard temperature and pressure, or standard pressure, which is 1 atm. Okay, this is how pressure cookers. Does any of your parents have pressure cookers? Your mom, or do they use them for canning, or do you actually cook meals? There we go. Okay, how it works is it traps in all the vapor in there, and it increases that vapor pressure so high that it increases the boiling point, which increases the temperature that stuff can cook, so it cooks faster because it's increased the temperature. That's how it works. Okay, so when it's boiling, the temperature at the boiling point remains constant even though you're adding heat. And so all that heat that's getting added is used to change the water into vapor, to overcome attractive forces. So we have a value that's called the molar enthalpy of vaporization, which is the amount of heat energy needed to vaporize 1 mole of liquid to a certain boiling point. And so you can use this to measure the attraction between particles, because the higher the molar heat of molar enthalpy of vaporization we have, the more polar, the more attractive forces are between the molecules, because it's taking more and more energy to evaporate or vaporize that substance. Okay, so we're going to use that as a conversion factor, because what the units for this will be, depends on if you're in joules or kilojoules. It will probably be in joules. Hold on. It'd probably be in joules per mole. And so we'll have a certain joules. Let's say it takes 32 joules to convert 1 mole of that substance. If we know how many moles of water we have, we could convert that into how much energy we're going to need to evaporate all of that water. That's how we'll use that. So freezing and melting, opposite end of the spectrum. Temperature at which the solid and liquid are in equilibrium at 1 atm. So we have the solid, you have to add heat energy, add some sort of energy to it to become a liquid, or liquid would give off energy to become a solid. Reversible equation again. The particle of liquid and solid at that freezing or melting point has the same average kinetic energy. Melting and freezing point is the same, so it's 0 degrees Celsius at 1 atm. What is it in Fahrenheit? 32? Okay. So we have another way to find the energy. Instead of molar enthalpy of vaporization, we use molar enthalpy of fusion, because if you think of fusion as two things fusing together, if you think of freezing, they're coming together to make a solid. You can remember it that way. But it's the amount of heat energy required to melt or freeze 1 mole of solid at the melting point. Okay, so those are the two most common. Boiling and condensation, freezing and melting are the common points that we look at, but there are also 2 other phase changes that can occur, and one is sublimation, changing state from a solid directly to a gas. Can you think of when a solid changed directly to a gas? chemical change, or if you're burning something. But that's a chemical change. Burning is a chemical change. What about dry ice? What is dry ice? You know what dry ice is? What? It's solid carbon dioxide. So it's a chunk of, it's solid, but it's carbon dioxide that they've cooled down so much that it becomes a solid. And then when you have it at room temperature, it just starts like have vapor coming off of it, steaming. I don't know. You have that kind of like the steam that we saw off the liquid nitrogen. Okay, it's what they use for like fog machines. It becomes foggy. Okay, so the dry ice would be sublimation. Goes straight from a solid into a gas. What about a gas going directly to a solid? Last couple of mornings we've had it on your car. They have to scrape off. Frost. Because frost is the water vapor in the air turns directly into a solid on your car or the trees or the grass or somewhere. Okay, so that's going from a solid a gas directly to a solid. So that'd be deposition. Sublimation and deposition. Okay, here's a problem that we're going to use our molar enthalpy of vaporization and fusion. Given that a substance has a molar mass of 259 grams per mole and 71.8 grams of that substance absorbs 4.03 kilojoules when it melts, calculate first the number of moles in the 71.8 gram sample. How would we do that? If I have 71.8 grams of the sample, how would I change that into moles? Right, because we'll have 259 grams per 1 mole. So we'll divide that. I don't know what the answer is. Someone have their calculator out? Let's see, a couple. What'd you get? 0.277? You guys agree? Okay. 0.277 moles. Good. So now how would we find the molar heat of fusion? What is the molar heat of fusion? So the energy required to melt 1 mole. So if we know that it takes 4.307 kilojoules to melt 0.277 moles, how would we find 1 mole? Right, we want our units to be in kilojoules per mole. So all we would have to do is take our 4.307 kilojoules and divide it by the amount of moles we have, which is 2.277. Okay. Kilojoules per mole. That's all you'd have to find. Yep. Another way we could have done it, if it takes 4.307 kilojoules to melt 2.277 moles, you could set up a ratio to have X kilojoules per 1 mole, and that would kind of give you the same thing, but you're going to end up just dividing them since it's 1. So this would probably be the easiest. Just use your units. Okay, you can do the same thing with molar enthalpy of vaporization. Just make sure you know which one. If you are evaporating something or condensing something, are you going to use molar molar enthalpy of fusion or molar enthalpy of vaporization? If you're evaporating, boiling, or condensing something. So that would be your molar enthalpy of vaporization. If you're freezing or melting something, you're going to use the molar enthalpy of fusion. Just make sure you know which one to use. Okay, and the last thing today is phase diagrams. We're going to graph some of the temperature and pressure changes, but it's a graph of pressure versus temperature that shows where the conditions where phases change. There's a couple, I'll show you an actual phase diagram here, but there's a couple points that we need to know where temperature and pressure, the triple point is where the temperature and pressure condition in which solid, liquid, and vapor all coexist. So there's a specific point where all three phases can exist at once in equilibrium. The critical point is kind of dependent on where the critical temperature and critical pressure is. But the critical pressure is above that point, the substance can't exist in a liquid state. And the critical pressure is where the substance cannot exist as a liquid state any higher. Yeah, you might want the difference between critical temperature and pressure. That'd be fine. Okay, so I think the next slide is a diagram. I can come back to this. So this would be what a phase diagram looks like. Now, it wouldn't be labeled like this, but right here in the orange area, this is where the water, is going to be solid. The purple or blue area is where it's liquid. The gas, this is where it's going to be gas. So this critical point is where the critical, and actually, I don't think this should be, whoops. This should go straight up here. And this side should be all green and this side should stay blue. Because the critical point is at the critical temperature, which you draw your line down to find your critical temperature, but you can't have any more liquid at higher than that temperature. So you really shouldn't have any liquid here, and you can't have the pressure where liquid can't form anymore either. But so we have our solid, liquid, and gas phases. So when you cross these lines here, you're actually changing state. So if we're going from a solid to a gas, that's sublimation. Deposition is from gas to solid. This is our triple point where all these three lines combine here at this certain exact. You'd come across, find your pressure and your temperature where that triple point is. So if you're a liquid to a gas, is vaporization, condensation, melting, and freezing. So those are, you can find, like at this certain pressure, let's say this is 1.5 atm, where is the boiling point? So you come across here, find where the boiling point is right here, and you'd come down to that temperature to find the temperature it would be. That's how you use those phase diagrams. So questions on any of that? We will be using Celsius, usually, yes. Okay, you have the rest of the period. You can work on your packet.